Okay, so this is the section about vibration measuring instruments we are going to use in order to do the measurements spring mass damper system inside a rigid casing, and it will be placed on a surface or on the uh, outside of a machine, and this is why it is called seismic unit that can measure the vibration of the ground or the surface. Okay, and then we derive the relative equation Z, which is x minus y, and this becomes basic citation. So we can put the equation of motion in terms of Z, which is mz level dot plus cz dot plus kz equal to m omega square y sin omega t. And then we can see the solution of this equation. We will not go further in terms of x because inside the seismic unit, you can measure the relative displacement rather than you measure x, because both are moving. The casing is moving and the mass is moving. So the only thing you can use or measure is the relative. And measurement is based on the steady state solution, not on the total solution. If you put damping, then the transient or the homogeneous solution will decay with time, and you will have only the particular solution, which is the steady state, which is this equation, Z equal to m omega square y divided by square root of k minus m omega square all square plus c omega square. And we can put this in dimensionless form and also the phase. And then the plot shows that there are two useful ranges of this seismic unit, which can be used at omega over omega and very much greater than 1. And here you can see all curves are equal to unity, so that z over y is almost 1. So it can be used to measure displacement. And the other area, useful area, is near 0. And all curves behave like omega over omega n squared, and then you can use this to measure the acceleration. So at this range, it is called accelerometer. At omega over omega n very much greater than 1, this is called seismometer. And then we started last time talking about each one of them. So there are two basic things, two sensors, seismometer and accelerometer. Seismometer is the instrument with low natural frequency. And in this case, we have Z over Y is almost 1. So the output of the seismometer is Z, but it is used to measure Y, and in this range, it is almost equal to Z. That Y is almost equal to Z. So we have the error factor is if the Z over Y value is deviated from 1, then that will be the error. Okay, if Z over Y is exactly equal to 1, then the error is 0. We can put, and I explained this last time, in general, okay, we, first of all, if example that we have to find the useful range of a given seismometer, useful range for a maximum error of 1%. Okay, so we have to check the peak. We need to check the peak if the peak is greater than or equal to the 1.01, because if the error is 1%, and here is an example of zeta equal to 0.6, the error factor will be either 1.01, because the error is the deviation from 1. So it is either 1.01 or 0.99. If the error factor, which is Z over Y, Z over Y is called the error factor. The equation, the equation we derive here. If Z over Y equal to 1, it means that y equal to z. So there is no error, right? And this can happen somewhere when there is intersection point with the line equal to 1. So here the error is 0 for this zeta equal to 0.25 or zeta equal to 0. For zeta equal to 0.5, the error is 0 here because at this point, at particular point, there is zeta that the error is 0 because z over y is exactly 1, equal to 1. And this happens only at certain frequency. But the useful range required mainly is from a minimum to open to infinity. Okay, so that is the useful range usually required for the sensor to be used. Okay, so here the example is zeta 0.6 and the error is 1%. Then z over y either 1.01 or 0.9 or 0.99. Okay, the deviation from 1. Okay, so which one to choose is we need to check at the peak. Okay, at the peak, if this error is greater than, okay, let me just put 2 lines. Okay, if this is greater than greater than 1.01, then it means that 1.01 is here, right? Because if the error factor at the peak, at the maximum, is greater than 1.01, then the 1.01 is below. And then the useful range will start from here. This is the useful range. And we let that the peak value, this is R peak, which is omega over omega n peak, that correspond to the peak point, is 1 over square root of 2, well, 1 over square root of 1 minus 2 zeta square. Okay, so here is what you should do. You check the error factor at peak. So if the error factor at peak at the maximum is greater than 1.01, then let z over y, which is the error factor, equal to 1.01, equal to, and solve for r, or solve for omega over omega. Okay, and there will be two values, as you can see from the graph. There will be intersection, there will be at this point, which is R1, and at this point, which is R2. If you choose R1 to be the useful range, the starting of the useful range, you will have error factor greater than 1.01, which is greater than the maximum required error. Okay, so in this region, in this area here, the error is greater than 1.01, greater than 1%. So you should use R equal to R2, and then you find the frequency. Okay, so from the error factor, the equation is equal to, this is 1.01, equal to, I will use R squared divided by square root of 1 minus R squared, all square, plus 2 zeta R squared. Okay, and zeta is known 0.6 for this example, 0.6. Then you can solve for R. And there will be two values, R1 and R2. Okay, suppose R2 greater than R1. Okay, you select, okay, we choose R2. Okay, and R2 equal to omega over omega n. or f over fn, then omega becomes R2 times omega n. And that will be the lowest frequency in the range. If on the other hand, we find that the error factor at the peak is less than 1.01. Okay, is less than 1.01. It means that 1.01 is somewhere here. Then there is no intersection with 1.01. We take 0.99. Okay, it means this is the graph, and this is 1, and here is the error factor, and 1.01 is here, which is not intersecting at all. And then we have 0.99, just to make my the proportionality is not. Okay, so if this is the error factor is less than 1.01, it means 1.01 is somewhere here, no intersection, and then this is 0.99. In this case, we choose the error factor equal to 0.99, and we solve for R. Which is omega over omega n. There will be only one value. As you can see, the intersection with the curve is only at one point. So this will be the error factor, the lowest. This is the useful range. Start from here. So you will put in you know that 0.99 equal to R squared divided by square root of 1 minus R squared all squared plus 2 zeta R squared, and solve for R. There will be only one value of R. The section is occurring only at one point. Okay, so this is for the seismometer and how to calculate the useful range based on the given error. Okay, so the other questions could be if the error factor of the seismometer is going to be used within certain range, what is the maximum frequency? What is the maximum error? If the given range is after the peak, then the error, the maximum error occurs at the beginning of the range. If the range is after the peak, after the maximum, then the maximum error occurs at the beginning of the range. As you can see from this figure, the maximum error occur here. Okay, this is corresponds to maximum error. Right, the error afterwards is less because the error is the difference. Okay, so this is the maximum error, which is in this example, it is equal to 1%. In this example, is 1%. So afterward, it is less. The difference is getting smaller and smaller. So the error afterward is less. If the range is given before the peak, then we have to check the peak. if the peak is greater than the error at the given, and we need to find two values at the beginning of the range and at the peak. If the range includes the peak, okay, in order to check the maximum. Okay.
So doctor, so we have to figure out the peak always, the error peak.
Yeah,
and then
yeah.
proceed with the
Yeah,
question.
if zeta is not 0, you have to figure out how much is the peak and compare the value of the error factor with the given maximum error. Okay, which is the error factor. It in this example is 1.01 or 0.99. If the maximum error is given 2%, then you check with the 1.02 or 0.98. Okay, so just as another example.
Doctor, if it's 2%, won't it be 2.01 and 1.99?
If a 2% maximum error is 2%, then the error factor z over y will equal to 1.02 or 0.98.
Okay.
It's always you have to add with the we subtract with the with the error factor, or add or subtract with the error factor, because the error is equal to 1 minus the error factor, or vice versa. يعني the error factor equal to 1 minus the error.
Okay, thank you.
Okay, either plus or minus. Here.
Yes.
Okay, the error factor is equal to okay, and based on the value at the peak, we select the proper value of the error factor. Okay, so for the accelerometer, the second type of the instrument is the accelerometer, which is used to measure the acceleration. So in order to do that, the initial frequency is very high. Okay, here the frequency in terms of in the its value will be in terms of the order of kilohertz, very high. Okay, in the seismometer it is in hertz, 1 hertz, 2 hertz, 3 hertz, 5 hertz. Okay, but here it is in terms of kilohertz, like 8,000, 10,000, more. Okay, so the error factor will reduces to omega over omega n squared. So Z is going to be equal to omega square y over omega n squared, because as omega over omega n goes to 0, we will have all the curves are behaving as omega over omega n squared, as you can see from this graph. Near 0, this is inserted here, a curve omega over omega n squared is inserted, and you can see that all curves are behaving as omega over omega n squared. So the equation for z over y is z equal to, when omega over omega n is very small, very close to 0, you will have z equal to almost y omega over omega n squared. And then the error factor for the accelerometer will be 1 over the square root. That will be the error factor. Okay, because z equal to y omega over omega n squared. If this is a true, equal, then you have no error. The error is 0, right? When z equal to y omega over omega n squared, it means that 1 over the square root is 1. And there are also a point at which that we have the error factor is equal to 1. So here is the error factor for the accelerometer. Not z over y. The error factor will be 1 over the square root of 1 minus omega over omega n squared or squared plus 2 zeta omega over omega n squared. So we have two error factors. Each instrument has a different error factor. The accelerometer, the seismometer, the error factor is z over y, the equation, the whole equation. For the accelerometer, the error factor is 1 over the square root. Okay, now we're plotting this equation, which is the error factor, for different values of zeta. Okay, the range, the useful range for accelerometer is measured from 0 and on. Okay, so useful range depends on the value, but for all the cases, the useful range starts from 0. And on. They start from 0 to a maximum. Okay, maximum frequency will be, the frequency ratio will be less than 1 for sure. In the seismometer, the useful range start from a minimum value open to infinity. Okay, as we saw there in the seismometer. Okay, somewhere I should write it, right? Okay, so useful range here in general. Does not start from 0. Okay, to infinity. Whereas in the accelerometer, this the useful range start from 0 to a maximum frequency. So they work in different ranges. The two sensors work at different ranges. So here is the error factor, the plot of error factor for different values of zeta. We will use the error factor to calculate the maximum error. Now you can see that when the error factor here is equal to 1, which is this line, the error is 0. For example, zeta equal to 0.6, the error is 0 at this point. Only at a specific value. The same thing for 0.6, the error factor is at a specific point. Here, if a frequency range is given, then you have to check that how much is the maximum error. The maximum error will occur at the end of the range or at the peak. Okay, so let's suppose we take zeta equal to 0.65, and let's say that calculate the maximum error from 0 to 0.7. What is the maximum error here? So the maximum error will be either at the end of the range or at the peak. So we have to check the error factor at peak and the error factor at 0.7 and compare the maximum. Which one is the maximum?
It's at the peak, right?
Depends, because for this example, it is almost 1.01. It is more than that, 1.05, maybe 1.015. Here it is more than 0.96. So this is more than 4%. This is less than 2%. So the maximum error is here at the end of the range. Okay. Yeah, you can calculate, substitute in the equation. Okay, the peak in this case occurs at a frequency ratio 1 minus 2 zeta squared, which is obtained from the error factor by R. You make it equal to 0. And this is in the formula sheet. R peak is occurs at square root of 1 minus 2 zeta squared. So you can first of all calculate R peak and then substitute in the error factor and find how much is the error factor. And substitute in the error factor at R equal to 0.7 and compare the maximum. Okay, so this is the way to calculate the maximum error if the range is given. Here, as you can see, the best one that can give you, there are different values of zeta here shown, our curves for different values of zeta. We have zeta equal to 0 is shown, and zeta equal to 0.7, and all those 0.6. The best range, the best one that can give you a bigger range is zeta equal to 0.7. As you can see, it is almost flat up to 0.2. You know, this is almost straight flat for zeta equal to 0.7, which means that the error, the maximum error within this range from 0 to 0.2 is going to occur at 0.2. Okay, as a comparison, the diagram shows that the useful range of the undamped accelerometer, which is zeta equal to 0, is somewhat limited. Like, as you can see, it is directly, it's going up. So the error is starting to increase as you increase the frequency ratio. However, with zeta 0.7 of this, using the same useful frequency range from 0 to 0.2, the maximum error is less than 0.01%. Okay, this is the maximum error. It means that if you want the error, not this is percentage. It means the error is equal to 0.0, and you put 2 zeros, right? This is 1 over 10,000. That is the error at maximum, okay, which is at 0.2. That is the maximum error with zeta equal to 0.7. But at the same range, when you use zeta equal to 0, the error is 4%. Okay, here the error for zeta equal to 0.7, the maximum error is 0.01% as a comparison. Okay. Okay, we will talk about the tutorial next time because time is over. Any questions?
No, doctor.
All right, thanks. All right, we'll see you inshallah next time.
Thank you, doctor.
Bye.
Assalamu alaikum.
Alaikum salam.